This is page 39, and we're going to simplify some radical expressions. Now, as a little review, we might mention that this, if we take away the radical sign, and this is 16 to the first power, this would equal 16, take away the radical sign, and then convert it into fractional exponential notation. So this is 16 to the 1/4 power. These two are equivalent. And the fourth root of 16 is 2, because 2 to the 4th power is 16. And here the square root of this is a perfect square, and this is 13. Now keep in mind here we're finding what is called the principal square root, because there could also have been a negative 13 that we squared to give us a positive 169, as there could have been a negative 2 that we have raised to the 4th power to give us a positive 16. In example 3, if we convert this from its radical form to its fractional exponential form, again we take away the radical sign, write our radicand as the base. The exponent to which the 10 is raised becomes the numerator. The index number becomes our denominator. And what is 10 divided by 10? It is 1. So this equals 10 to the first that we don't write. So a general pattern is anytime a radicand is raised to a power that is the same as the index number, then it just becomes the radicand, which is now our base. Now in example 4, we had said earlier we can rewrite this as a product of radicals, and under the first radical sign we can put any perfect square that we have there, and then what is left under the other radical sign. So keeping in mind there is a 2 here, so this is just going to become 4, removing the radical sign. This is 2 over 2, and the square root of 4 we know is 2. So this gives us an 8. And for example 5, we can write it up here. The square root of 48, dividing that into parts that are a perfect square, and those parts that are left over, we get 16 times 3. And the square root of 16, we recall, is 4, the square root of 3. Before we leave this page, we might also mention that if we were to expand 4 to the 3rd power, we get 64. And then the square root of 64 is 8. So showed you, in a sense, 2 ways to do this. On page 40 now, we are asked to rationalize the denominator. Now, for this, we're going to use a tool that's called the Radical Conjugate. So what is the conjugate, let's say, and let me write this a little bigger here, of 1 plus the square root of 2. Well, the conjugate of anything we said earlier was, and we're going to make this in the form of 1, it's what we have here, but it's opposite side. So here now, this and that are conjugates. So we multiply our numerator, and this becomes 8 minus 8, the square root of 2. And then our denominator becomes, as we multiply our first, this is a 1, and this is a negative square root of 4, and a square root of 4 is 2, so 1 minus 2 is a negative 1 in the denominator, and in our numerator it becomes 8 minus 8, the square root of 2. But we don't usually want to have our denominator negative like this. So I can place that negative sign rather than here in the denominator. I can place it up there in the numerator. And then this is just a positive 1 that we can eliminate here. And so, as my final answer, this is going to be negative 8 plus 8, the square root of 2. Now in this process, what we have done is taken a number that was irrational in the denominator and made our denominator a positive 1, which is now rational. So we have rationalized the denominator. So for this one, we're going to multiply numerator and denominator by the radical conjugate, which will be 2 minus the square root of 5, 2 minus the square root of 5. So our numerator becomes 12 minus 6, the square root of 5. And our denominator, as my wife just called me, 2 times 2 is 4. And again, if we just take the square root of 5 times the square root of 5, which is the square root of 25, this is a negative square root of 25, which becomes a negative 5. So following that same procedure, this is going to be a negative 1 down here. So if we just change the signs up there, negative 12 plus 6, the square root of 5, we have rationalized this denominator. So as we do these next two, we should give you time, of course, to work on this. What would be the rational conjugates for these? And remember, it's opposite signs. And here we're just multiplying these by a 1. So whatever is in the denominator, we have in the numerator. And let's see what you get. So as we FOIL the top, this is a 125. Our inners become a negative 5, the square root of 5. My outers, 25, the square root of 5. When I do the subtraction, I end up with 20 the square root of 5. And when I go a negative, square root of 5 times square root of 5 is negative square root of 25, which is a negative 5. Now my denominator, as I FOIL this, I get a 25 minus 5, which is going to be a 20. And I'll just save a little room, and then I have a 125 and a 5, negative 5. This is going to give me there, subtract 5 from 125 gives me a 20 there. Now, the way to simplify this is I'm going to separate this a little bit into two terms and put my 20 under each one of these. There you go. So now this cancels into this and I get a 6. This just cancels and I get plus the square root of 5. So this one was a little more tedious, and of course this is the answer they have in our text. And we'll do this in parts also. As we FOIL this, we get a 36. As we do our outers, we get a negative 36 square root of 2. Our inners, a 1 square root of 2. Do the subtraction and end up with a negative 35 square root of 2. And when we do our last, we get a negative square root of 4, which is negative 2. Now our bottom, as we FOIL this is going to be a 1. And this is going to be a minus 2. So our denominator here becomes a negative 1. So we can erase that a little bit, save room. Now we're going to combine our negative 2 and 36 and get a 34 there. Now again, we don't want to have a negative in the denominator, so we're going to make this a negative and this a positive. And that's our answer. We have rationalized the denominator, and it's quite a detailed process. In example 5, we want to look at what are our radical conjugates. We'll set this up little by little. So we have the square root of 2 plus 5. Square root of 2 plus 5. Remember, this is just a 1. We can multiply anything by 1. All right, let's do the FOILs. So when we FOIL this, we get the square root of 14. When we do our outers, we get 5, the square root of 7. Our inners, 5, the square root of 2. And then our last, we get a positive 25. Notice there's nothing we can really combine there. So in FOILing the conjugates here on the bottom, we get square root of 2, square root of 2. I saw a little error there. Square root of 2, square root of 2 is square root of 4. Square root of 4 is 2. Okay. 2 minus 25 gives me on the denominator here a negative 23. And again, they don't like to have this as a negative. I see our book is going negative 1/23 times all of that. Rather than put that there, I would have changed all these signs up here and had a positive 23. All right, two different ways to do it. Both are satisfactory. All right, let's go on. Now, as we go on to page 41, we're now going to bring to closure a lot of things we've been working on up till now, and that is solving quadratic equations by factoring. And you might say, if you are solving quadratic equations by factoring, what is the underlying principle? Well, we had mentioned in lecture that if we have A as a factor, and it's times B as a factor, and that equals 0, the only way this can be true is that either A equals 0 or B equals 0, or they both equal 0. This is called the zero of the principle of the zero factor. That in order for a product to be 0, one of the factors need to be equal to 0. So here we see a binomial, which we could think of as A, and this binomial that we can think of as B, and we have A times B equals 0. This way, the only way it can be true is that either this factor A, which we now know is y plus 3, is equal to 0, or this factor, which we're replacing B with, y minus 4 equals 0. What would be the value of the y to make this a 0? Well, we just solve it, and we get y transposing the 3 gives us a negative 3, or y equals transpose the negative 4 gives us a positive 4. And if we put a positive 4 there, this is 0. And if we put a negative 3 there, this is 0. So our values then, in solving this, is that y could be a negative 3, comma, or a positive 4. Now, these are factored already, and they equal 0. So they're in this form. So now we could just shorten this and say, well, this equals 0. This equals 0. Here, z will equal a positive 7. And the same thing there. Z equals a positive 7. When both answers are the same, we only write it once. Now in example 3, they went from some easy ones to some that are more challenging, because this is how we're usually going to find them, that it's a trinomial that's equal to 0. And this is what we say is in our standard form. ax squared plus bx plus c equals 0. So we have a trinomial that equals 0. This is standard form of the quadratic equation. Now to solve it from this form, we have to factor this. So that's what we're going to do here. Factor this. Now our a value is a 1, so this makes it a little easier. This is going to be n and n. And I happen to know the factors of this are 11 and 13. And since we need a negative middle term, this will be negative, and this will be positive. So I now equal each of these. N minus 13 equals 0, or n plus 11 equals 0. And then we just solve them. Transpose, transpose, and there are our solutions. A negative 11 and a 13. And if you were to put that in this original equation, these values would make this a true statement. Okay, jumping down to letter or example 4. Do you recognize what we have here? And if you said the difference of perfect squares, that is correct. So they will factor into its conjugates. And again, g plus 11 equals 0, or g minus 11 equals 0. So here g equals a negative 11, g equals a positive 11, and these are our answers. And you see now where factoring came into the situation. And of course, this is the work we want you to have on your blue sheets and in your homework log. And once again, they actually factored that trinomial that was there, and it equals 0. The key is that it has to equal 0. So we get 2x plus 4 equals 0, or 3x minus 5 equals 0. So here we transpose the 4 to a negative 4, and then divide by 2. So this is going to be a negative 2. And here we transpose the negative 5 and divide by 3. And these are our solutions. Okay, so we're running 22 minutes, so we'll close this one out here and pick up later.